Thank you for coming today. So this lecture will be recorded both there in the Marius is taken care of, but then it will also, I don't know why it's see, I don't know what that is. I'm also recording this on my computer, and so I'll be able to upload this lecture online for any peruse. And of course, you're welcome to email me with any questions or ask the TAs as well over the course of the course. So as many of you know, this is an experiment. This is the first time we're doing this lab module. So in part, we're relying on all of you for a little bit of feedback. To our knowledge, this is the first instance of a laboratory ever taught at MIT that focuses on the chemistry, and particularly the electrochemistry of renewable energy. So we think this is exciting because it's really, one, an experiment. We planned this lab for the better part of a year, and we're now happy to be deploying it to the MIT community for the first time. And so we hope that you'll get something out of it, and we hope that it will really be a basis, hopefully, for a broader effort to integrate topics like this into the MIT chemistry curriculum. So you really should kind of feel, I think it's interesting to be one of the first to kind of see this. So we really look forward to your feedback in ways that we can improve this module in the future. So part of the genesis of this was the fact that our own research group, my research group, focuses on the chemistry of renewable energy, and particularly on electrochemical approaches to storing renewable electricity. And so we wanted to create a module that reflected both my group's research, but also just the general consensus now that chemistry plays a central role in solving what are, in my view, the biggest challenges society faces in the 21st century, which are primarily problems that relate to energy, sustainability, the environment, particularly as it relates to, for example, the emission of CO2, harmful greenhouse gases, how we're going to essentially come up with an additional 50 terawatts of power by the second half of this century. These are all questions that fundamentally relate to chemistry, I feel, and particularly how electricity and chemistry relate to each other. And that's really what this entire module is about. So I feel very proud to be rolling this out to the community, and I hope you'll find it very, very valuable. So the focus of the lab really is on understanding the fundamentals of chemistry that occurs at polarized solid-liquid interfaces. And I'll explain what that means in a moment, but every one of you is carrying around a device that relates to the chemistry that you're going to do in this lab. In fact, it's probably in your pocket. There's several right here in this laptop. So every battery you've ever worked with, every device of that sort, like the battery that's in this phone, for example, are all electrochemical devices. And fundamentally, knowing the chemistry that's occurring at the electrodes in these devices can allow you, independent of what you want to do later on in life, to really sort of understand what the fundamental science challenges are to, for example, making a laptop battery that lasts for a year rather than a day, or storing electricity on the terawatt scale rather than on the watts scale. So these are the fundamental problems society faces, and we're really going to discuss a lot of them at a fundamental level, at a chemistry level in this module. So what's really going to be the focus, right? So the focus really is a module that discusses the chemistry as it relates to a sub-branch of chemistry known as electrochemistry. And electrochemistry is fundamentally the study of how electrons can be used to drive chemical reactions. And these are so fundamentally important to how society functions, most people don't even realize that. So how many of you have ever ridden an airplane? I think all of you. An airplane would not exist without electrochemistry, because the material that comprises the majority of an airplane is aluminum. And aluminum is not a naturally occurring mineral, aluminum metal, that is. In fact, the energy that's needed to make aluminum is supplied entirely by electricity. And it's done so at the interfaces between a solid and a liquid. And so, for example, aluminum smelting is done with electrochemistry in these enormous plants that make all of the aluminum society has, right? So before the advent of electrochemical technologies, there was no aluminum. And as a result, because of that being such a lightweight and strong material, we wouldn't be able to do a lot of the things society does currently. This is just one example, right? It turns out actually that one of the earliest applications of electrochemical technologies was in a process known as electrowinning. Winning sort of refers to the fact that you're refining or obtaining pure forms of a lot of materials. And this was originally done in aluminum, but if you think about it, it's really been done for a lot of things, right? So where we get lead for lead acid batteries or for a host of other applications, where we get refined copper, gold, silver, zinc, aluminum, chromium, and really virtually almost all materials in the periodic table that we obtain in pure form currently is made through an electrochemical process, with very, very few exceptions. So I just want to highlight to you how impressively important electrochemical sciences are, and how how shocking it is that we don't teach people more about this field and this science, right? So how many of you have ever had a class in electrochemistry? How many of you have ever had a lecture in electrochemistry? So, right? A very, very small number, right? And this is MIT. We're supposed to solve the world's problems, right? And so I think that this class is so fundamental to how we begin to change the culture at the Institute to be able to do this. So, more recently, of course, electrochemical systems play a fundamental and perhaps the most important role in enabling a renewable energy future. And the reason for that is that most renewable energy sources that people are considering as viable in the future are intermittent renewable energy sources. So for example, if I want to have a solar farm or a wind farm to power MIT, the problem is that at nighttime when I need lights on in the lab or in a classroom, the sun isn't shining or the wind may not be blowing, right? So the inherent intermittency of electrical generation by renewable sources mandates strategies for storage. And if you want to store electrons, the best way to do that is to pack them in chemical bonds. And the way to pack electrons into chemical bonds is to have those electrons do chemical work. In other words, to do chemistry. And that really is where the centrality of electrochemistry is in terms of doing energy storage. And so here's just some examples, right? So you can run fuel cells or electrolyzers that, for example, have a fuel in and have an airstream in and generate electricity. These actually operate in many transportation buses across the globe and have been doing so for decades actually right now, but this is still not yet a technology that's able to scale at a global level. We don't have fuel cells, for example, in all of our cars, and that's largely because the costs and the development of the materials and catalysts needed to do the electrochemical reactions have not advanced far enough. So on some level, this is not on some level, on a major level, enabling these future energy technologies relates fundamentally to the basic science of understanding what happens to catalyze these reactions at these interfaces. And actually, the cool thing is, in this very lab, you're going to make devices and understand catalysts that do the very same reactions that occur in fuel cells and electrolyzers that are really going to be the basis of what will be a future dramatically altered renewable energy. You can do a lot more, right? So you can, for example, have a lithium battery, or not necessarily a lithium battery, but many other types of batteries that are in your laptops and smartphones. And one of the first modules we're going to do in the class is actually to examine an operation of a very simplistic battery that you'll construct, and you'll make, and you'll see the power output from it. You'll be able to charge and discharge it, and be able to know something about the nature of the reactions occurring, and understand the complexity of these systems. Of course, in the modern era, there are a lot of things. My own group does a lot of work in this area and understanding more complicated electrochemical processes that are just emerging, right? Wouldn't it be awesome if we could use renewable electricity and convert pollutant CO2 back into a fuel? That's something our group is actively working on. We've made a lot of progress in this area, but this is really comes down to understanding the chemistry that occurs at polarized interfaces. And we're going to talk a lot about that in this lecture, and that's really what you're going to learn a lot about over the course of this project. So the field of electrochemistry is really quite old on one level, but on the other level it's also very new, right? So the reason I want to stress that dichotomy is that it's old in the sense that phenomenologically, I guess by trial and error, people figured out that you could use electricity to do chemistry. And basically the first person who really put this on a solid foundation is Michael Faraday. And Michael Faraday is widely regarded as essentially the father of electrochemistry. He, for example, discovered fundamental laws of electrolysis that we'll discuss in this class. So if you want to electrolyze something, essentially use electrical work to drive a chemical reaction, you need several key things. You need a cathode. At a cathode, a reduction reaction occurs. You need an anode. At an anode, an oxidation reaction occurs. You're pulling out electrons from molecules. At a cathode, you're putting in electrons from molecules. See, coined the terms electrode, and believe it or not, he coined the term ion. So this was a very prolific man, Michael Faraday, and actually had a very, very limited education. He never actually went to college. He discovered the first electromagnetic motor, induction motor. He discovered benzene, liquefied chlorine for the first time, made the first carbon-chlorine bonds that have ever been made. Right? He made chlorine. How would you guess? What allowed him to make chlorine? Chlorine is not a natural material that exists in the biosphere. He made it electrolytically. So he figured out how to use electricity to make and break bonds that could otherwise never be made and broken. And as a virtue of that, he made a molecule, a substance that's just never been isolated before, period. And so it's just an illustration, right? He's the first to study gold colloids. So gold colloids are small particles of gold that are the reason that stained glass windows are the color that they are. But he actually was the first to actually synthesize them, again, using essentially electrochemical methods. He discovered that. And again, prolific amount of effort that he did, but the one thing I have to say to all of this, right, is that to a large extent, though all of this is fundamentally on some level chemistry, at least most of these things, the actual nature of the reactions that are occurring between the electrode and the solution, where the rubber meets the road, even at Michael Faraday's time, and even till now, 150 years later, are still very poorly understood. So what this module is going to do is give you an introduction into how we think about and try to understand the reactions that occur between an electrode and solution, and how to understand that at an atomistic and molecular level. We now have an unprecedented ability to look into the nature of those reactions in a way that Michael Faraday would never even dream. Remember, he did all of this before the concept of an atom was even made, right? He did this before the concept of quantum mechanics, or the nature of the electron clouds, or the orbitals that are involved CO2 molecule was even known about, right? So this was all done phenomenologically well before our sort of very refined knowledge now of the nature in which chemistry actually happens. And so there's been a sort of rebirth, a revisiting of many of these concepts at a different level, at a level that is immediate. So I want to point out certain books that you may want to consider thinking about using as reference. A lot of them are available in the library. For example, this one I particularly favor from Gileadi. It's called Physical Electrochemistry. It's not too expensive. If you're really interested in the subject, it might be worth buying on Amazon. But this gives a very, very good introduction in a far more expanded sense than I can do in this 1 hour on some of the topics that we discussed. Okay, so the first thing we have to appreciate, right, is that electrochemical reactions are fundamentally different than reactions in a current solution. So if I mix reagent A and reagent B and I make a reaction to go to reagent C, right, I know some of the key features that matter for that. Well, first off, for reaction A and reaction partner A and B to get together to make C, they have to collide first, right? They have to collide and do a productive reaction. So what is the analogy of that at an electrode? Well, if A and B are both soluble, dissolved molecules in solution, their collision and how that occurs is relatively facile. But electrochemical reactions are inherently interfacial reactions. By interfacial, I mean they're between two phases of matter. They're between a solid phase, that is a conductor, that can move those electrons from the external circuit to that surface. And the reaction occurs at that boundary, that region between that electrode and that solution. Right near that electrode is where all the chemistry happens. And the entire module will focus on understanding the nature of that chemistry that occurs at this solid liquid phase boundary. So in order for reactions to occur at this phase boundary, first you can think about it in this overall sort of cartoon. You have an electrode. When you put a charge on that electrode, which we call polarization, you polarize it as in adding charge, then those charges accumulate and there's a counterbalancing of ions in solution. And that counterbalancing of ions generates an interfacial field. But the key features are that this interfacial field is on the length scale of a few nanometers to maybe a few angstroms. Whereas the bulk of the solution, right, in many cases maybe on the order of macroscopic length scales, millimeters, centimeters, etc., right? So things essentially have to diffuse from the bulk through what we call a diffusion layer to that solution to be able to do the actual reaction. This introduces some inherent complexities of electrochemical reactions that don't exist for simple molecular reactions existing in solution. But the advantage, the salient and unique advantage, is that I can dramatically alter the driving force for this electron transfer reaction simply by varying the potential I apply to the element. And that is so enormously powerful because you've learned since freshman chemistry that if you have reactant A and reactant B get together, there's a certain thermodynamic driving force to make reaction C. What you have in electrochemical systems is that thermodynamic driving force is no longer a fixed value, but a variable value. And that is enormously powerful, right? That's how we extract energy and put in energy into balancing molecules in electrochemical systems. Okay. So we can think about this in sort of a cartoon, right? So what we have here is a situation where we have what we call mass transfer. So if you have some oxidant or reductant, right, in the bulk, it has to essentially move, migrate. It has to diffuse, if you will. And convection can be used. You can force it to move by flowing the solution really rapidly, for example. But it has to move to the electrode surface. Now, when it gets to that electrode surface, there could be processes that occur that transform this bulk. Right, a molecule could shed its solvation shell, or pick up a ligand, or rearrange, or something like that, right? All of these are possibilities. And then you're going to have a reaction that may involve that molecule, say that substrate molecule, engaging in an interaction where it actually binds to that surface. And the binding to that surface may then initiate a situation where electrons get transferred. And that electron transfer then can then lead to a desorption, and the process can repeat, right? Now, not every reaction has to proceed through all of these. For example, some may engage in electron transfer without actually binding to the surface. We call that absorption and desorption. They don't need to necessarily do that, but in certain cases they will. And so we'll talk about that. And electron transfer actually occurs at the surface. So what are the fundamental components that describe an electrochemical cell? Right? So an electrochemical cell, what you're basically going to be working with for all of the laboratory, except for probably the one experiment on batteries, is what we call a 3-electrode electrochemical cell. This consists of what we call a working electrode, designated here, working electrode. It's working because this is the electrode that you care about. And you've set up your system in such a way that all the other elements are in place, so that the only thing that's controlling the chemistry is what's occurring at this boundary, this interface. And how this is achieved is essentially by having a power supply. And that power supply is in the potentiostat that you'll work with very shortly in lab. And that power supply will drive current flow from the working electrode to the counterelectrode, or if it's a reduction reaction, from the counterelectrode to the working electrode. And of course, there will be an ionic current through the solution that will complete the overall circuit, right? So ions will flow through there. There is also a 3-electrode. That 3rd electrode is what's known as a reference electrode. The reference electrode will essentially be the value against which you will measure the potential of the working electrode. This is a key difference, right? In electrochemical systems, we talk a lot about potential. But potential is not the same as voltage, right? Voltage is the separation between two potentials. Potential is actually the value of this relative to a known redox couple with a known. And so all potentials need to be referenced to some standard value, and you'll repeatedly do this over the course of the day. But this reaction, whenever it's occurring, you can determine the thermodynamics and kinetics of it by monitoring, for example, the rate of electron flow and the potential necessary to be able to drive that. Of course, this is enormously powerful. So first, let's understand the thermodynamics of interfacial reactions. What are the things that control the driving force? And this has already been tabulated for you for a wide variety of reactions. For example, we take the reference scale for potentials to always be the conversion of protons to H2. Just by convention, we have chosen that this particular reaction, taking 2 electrons and 2 protons and making H2, will be defined as 0. And from that, you can determine what all of the other reactions will be. And all of them will have different amounts of electrons and protons, and that will correspond to a given potential. And I'm literally only taking a very, very small section. If you go into a CRC handbook, you can find literally hundreds and hundreds of these reactions, and many more that are not actually. The point is that if I want to, say, for example, reduce iron 3 by 3 electrons to iron metal, because its potential resides negative of the value for hydrogen, what does that mean about hydrogen's ability to reduce iron 3 to iron 0? Well, if I take iron 3 and I did a thought experiment where this iron 3 get reduced to iron 0, No, right? And the reason is no is because this is telling you how reducing the hydrogen is. So all the potentials that are more negative of this value, hydrogen is not potent enough of a reducing agent to reduce those. But of course, for all the reactions I'm not showing that are positive of the hydrogen is reducing enough to do the reducing. Okay, so that's just kind of an understanding. I want you to have a qualitative understanding of what will reduce what by virtue of what potentials. You can go on and on. There are a variety of redox couples. The Nernst equation essentially describes how the potential of a given electrochemical half-cell reaction correlates to parameters of the solution. Again, we're only talking about thermodynamics. We're not talking about kinetics. We'll talk about that in great detail in a moment. What this is essentially saying is that if you take the thermodynamic potential, these are these values known as E0. E0 is simply denoting that this is the potential if all of the constituents in this reaction were at unit activity, right? That means that if I had 1 molar calcium ions in contact with solid calcium, this would be the potential of that reaction. But the Nernst equation allows us to ask, well, what happens if I lower the calcium ion concentration by 1 order of magnitude? Would that make this potential more negative or less negative? First off, what does it mean? If I say a potential is more negative, is it harder to reduce the calcium or easier to reduce the calcium? Harder. Yeah, okay, great. So if I have less calcium around, will it be harder to reduce or easier to reduce? Harder, right? If I have less calcium, it's harder to reduce because this equilibrium will be shifted in this direction. Right? Or you can think about it as I have less around, so I have to put more energy to be able to reduce them. So there's fewer of them. If there's a lot of them, the chemical activity is very high, I have to put in very little energy to reduce them. So if I lower the calcium ion concentration by 2 orders by an order of magnitude, that will cause this potential to move more negative. And that's reflected here, right? So if you look at the Nernst equation, and it's written in a form for reducing reactions where essentially the denominator, the numerator here is the products, and the denominator is the reactants, right? So you can work out the math here. If you lower the calcium ion concentration, that will cause this potential to move more negative. Okay. So the key thing we realize here is that in electrochemical systems, you can modify the rate of the reaction, the current that's flowing, or you can modify the potential that you apply to drive that reaction. But you can't simultaneously vary both, because changing the potential will change the chemical energy of those electrons, and that will augment the rate of the reaction. Or you can simultaneously hold the rate of the reaction constant and let the potential float until it meets the necessary value. So on the one hand, this is really powerful, right? Because you can systematically augment the driving force and look at the rate, or you can augment the rate and look at what the necessary driving force is. This is unparalleled in chemical systems, right? Imagine if I told you I wanted molecule A and molecule B to react together. But I wanted you to flip a switch and make them react so that only 10 molecules react between A and B per second. Could you do that? Right? If I put molecule A and B together in a flask, they're going to react at the rate that they want. I can't turn a dial and say I want 10 of them to react in a second, and then I want 100 to react in a second, and then I want 1,000 to react in a second. But in electrochemical systems, you can actually do that. You can set the rate and have the potential float to be able to match that. Very, very powerful. Okay. So this is what I'm saying. You can set the potential and read the rate, or you can set the current and accept the necessary potential. So let's understand a little bit more about the actual electrochemical cell, right? So what this electrochemical cell looks like, so you have a working electrode and counter electrode, and I'm simply redrawing this. Then you have a big power supply here that's applying a certain voltage differential, and that voltage differential is causing an accumulation, in this case, of negative ions here and countervailing positive ions. And of course, the opposite is happening, an equal and opposite charge buildup on the counter electrode, right? Since all these negative ions accumulate here, where did they all go? Well, these negative ions came, or these electrons came, from being pulled out of the counter electrode. And as a result, there's a countervailing charge here. Now you might ask, where exactly is the potential in the cell? Is the potential uniformly distributed across the cell, or does a lot of it vary right at the electrode surface? So it turns out that a lot of it actually varies right at the electrode surface, because
there's a lot of ions that have been moved from the bulk to the solution, the surface, in order to accommodate this what's potential gradient. And so if you plot potential as a function of the ionic current path, in other words, ions are moving in solution between these, and this is not a plot, right? The solution can move around this reference electron. I'm just showing this as a diagram. In solution, if the ions can move with relatively little inhibition to their flow, and this is not a perfect approximation, what you would expect to have is most of the field gradient or the potential gradient fall right at the electrode surface. And these fields, by the way, are extremely high, on the order of 1 volt per nanometer. Those are the highest fields in chemistry. Right? These are literally the highest fields that a molecule can ever experience, exists at the surface of a liquid. And that's why this is most powerful. Now, in reality, right, the ions don't move through solution with no drag. And because they have some drag, that causes a resistance, right? Resistance is really the impedance to the flow of charge, right? In a circuit that's electrons in a wire, because the electrons can scatter off the lattice, they don't flow through perfectly. And as a result, there's resistance in a copper wire. Now in solution, there's a lot more resistance, right? Because when the ions move, they essentially have to scatter across the solvent molecules. And so there's a drag. And this is related to viscosity, et cetera, all those things. But fundamentally, there's a resistance to the flow of ions, and because there's resistance to the flow of ions, that behaves like a resistor. Very simplistically, it behaves like Ohm's law. It behaves like a resistor. And so because of that, there is what's known as an IR loss, right? So Ohm's law states that the voltage drop is related to the current times the resistance. So you can measure the resistance of that solution, and that voltage change, the delta value between what's right near the electrode and what's measured at the reference electrode, is that IR loss. So when we talk about IR loss, we're referring to a potential, and it's related, of course, in this case, to the current. So if I vary the amount of the current, the magnitude of the IR loss is going to change, because the I has changed, even if the R remains constant. Let's look a little more closely at what's actually happening at that electrode surface, right? So what I'm showing right now is a picture where we have not charged the electrode at all. This is what's known as the potential of zero charge. For every electrode, there's a hypothetical potential I can apply, where that potential would be such that there would be no excess of charges in that electrode. It would be just what it would be natively in vacuum without adding any electrons, or taking out any electrons. And this is known as the potential of zero charge. This is not the same as what's known as the open circuit potential, which you'll measure in many of your cells, but it's a hypothetical construct. It's in reality true, and you can measure it in certain cases, and will be true for every electrode, but this is essentially the potential of zero charge. So if I have this, right, because I've not accumulated any charges, all the charges in solution are essentially just free floating, right? There are equal number of positive and negative charges, and I put some salt, electrolyte, into the solution in order to allow for this ionic current to flow. So once I apply, I know you want to see that again. So when we've applied a bunch of negative ions here, right, what's essentially caused that to occur is a lot of positive ions accumulated at that surface. Now, because positive ions are accumulated here, there's another layer with some negative ions, and then another layer with some positive ions. But eventually, right, as I go more and more layers away from the surface, it begins to look a lot more like the bulk of the solution. And so this is what is known as an electrochemical double layer. Essentially, it's a region where there's a charge on the electrode surface and a countervailing charge on the solution side. We can write more detail to this. There's actually several pieces to it, what's known as a compact and a diffuse double layer, but we don't need to discuss those subtleties at this moment. The point I just want to stress here is that this buildup of charge at the surface, one, leads to current flow, right? Because when I put in these electrons, they're coming in from the external circuit, so that's a flow of current. But this current flow is what we refer to as capacitive current. It is establishing the fact that that interface looks more or less like a capacitor. And so you can think about it as though every time you turn on and ramp the potential of your electrode, before you do any chemistry, you're going to have to charge up the electrode, which is synonymous with charging up the capacitor. But this is a very special capacitor, right? Because it's not a capacitor you look at as a solid-state device in physics. Those capacitors are rigorously capacitors, which is to say that only under a very, very high voltage excursion will they break down. But this interface is a leaky capacitor. And the leakiness of that charge is what is doing the chemistry. Does that make sense? You charge up a system, it's like a parallel plate capacitor. But if I have a normal parallel plate capacitor in physics, even if I apply a pretty high voltage, there is just going to be buildup of charge, but no charge is going to zip across from one electrode to the other. But here, though, that separation is this teeny little layer between the electrode and the solution. So electrons can zip across, and that leakiness is what's giving rise to the actual current you're going to measure in a reaction. So before we decide to do any reaction of interest, right, we'd like to know what the region of possible potentials are for the solvent we're going to use. So choosing the solvent is important, and one consideration that's relevant is what is the window of that solvent? Because ultimately, I'm not going to be able to drive a reaction beyond the potentials where the solvent itself, if you will, breaks down, right? And that breakdown of the solvent is a chemical reaction of that solvent to decompose it, right? In the case of water, it would be literally to split the water, to turn it into hydrogen and oxygen. Now, some cases you might want to do that reaction, but in some cases you may not want to do that reaction. You want to do some other reaction. But if that other reaction resides outside of the potentials where water breaks down, you're not going to be able to observe it. And so these things have been tabulated. You can determine a little bit more about this. So I mentioned that there's this reference electrode. So what are the reference electrodes that are viable, right? So the most important criteria of a reference electrode is that you need it to be one where it's, the term that we use is known as ideally non-polarizable, right? So the electrode, when you apply charge to it, is going to obtain a polarization. Its voltage is going to be, its potential is going to be different than the solutions. What you like to do upon passing some charge to the reference electrode is that no matter how much charge you pass there, its potential remains fixed. Because if its potential changed, it would no longer be a reference, right? You want its potential to be the same, irrespective of what you do to it. And this is what's known as ideally non-polarizable. And there are a number of different reference electrodes. The main ones that we'll use in this laboratory probably, it's a silver chloride is the main one we use, probably. So silver chloride electrode, and this is telling you what the known values of the potential of this electrode are relative to that universal reference, that normal hydrogen electrode. So you'll need to correct a lot of your data based upon these conversion factors. You'll also use in non-aqueous systems what's known as a pseudo-reference. Now, pseudo-reference is essentially an electrode that can serve as a reference insofar as it doesn't drift in potential over the time scale of the measurement. But because it's not a pure reference, that is, that it has a fixed potential, you need to independently and routinely calibrate what the value of this reference is by putting in an internal standard. And usually that internal standard is some molecule that can be oxidized or reduced to known potential. And in this case, it would often be with ferrocene redoxide. So you'll do that. Okay. So if I'm describing electrochemical reaction, right, the reaction at the interface is going to be convoluted between the thermodynamics and the kinetics of the reaction. And more broadly speaking, this is given by a sort of master equation that is useful, but actually doesn't give you too much insight. It's what's known as the Butler-Volmer equation, which is basically stating that any potential that you apply, and I should be careful here, right? So there's a lot of lingo here, so let me just run this. This J here is current density. It's current per unit area. J0 is the current per unit area that you would do as a thought experiment if you were right at the thermodynamic value. Then you have two exponential terms that you can think about as the exponential terms that relate to either scanning positive of the E0 or negative of the E0. If you scan positive of the E0, you're going to get one of these terms to dominate. If you scan negative, you're going to get the other term to dominate. Now, what terms in here denote the potential? So the potential is denoted by this term eta. And eta is what's known as an overpotential. So it's the same as a potential, but it's just a potential difference between the thermodynamic value and the value you're applying. So if the thermodynamic value for hydrogen evolution is 0.00, and I apply negative 400, what's my overpotential? 400, right? 400 millivolts, that's how much I've applied, negative of the value. Right? So that's the overpotential. And if I'm 400 millivolts negative of a hydrogen evolution reaction, The other reaction, because it's positive in the exponent for that overpotential value, is going to drop out to 0. And so what this essentially is doing is balancing the two half reactions, one on one side and the other on the other side. And to kind of show this a little more diagrammatically, what you can see here is that as you increase the overpotential for whatever reaction based off of the 0 value, one reaction will take off on one side and potentially the other reaction will take off on the other side. Now, not necessarily will you always work with a catalyst that will be able to catalyze both this reaction and this reaction. And so you may only observe catalytic reactivity on one side. But nonetheless, the exponential dependence on potential and reaction rate is something that is the key thing you need to appreciate. Here's another way to think about it, right? Is that essentially as you polarize more, you can see an exponential dependence on the rate of the reaction versus an applied rate. And so this is increasing our potential, and eventually you get to a point where the catalytic rate increases. Okay, so you'll take, even to do referencing, you'll take what's known as a cyclic voltammogram. So what a cyclic voltammogram essentially consists of is an experiment where you polarize in a linear ramp the potential versus time, right? So everything I've talked about so far can easily be extrapolated into a system where if I plot, potential here versus time, the descriptions I gave would be perfectly reasonable in a situation where I simply hold the potential constant in time. Right? If you hold the potential constant in time and measure the current, that's a technique known as chronoamperometry. Chrono meaning time, and amp meaning measuring current. Right? Chronoamperometry. Another technique you're going to use potentially in certain cases is what's known as chronopotentiometry. That's when you're going to do a similar experiment where you have time on this axis, and you're going to tell your potentiostat to hold the current, I or J, they're used interchangeably, and hold the current constant. So that's called chronopotentiometry, because chrono meaning time, but potentiometry meaning I'm measuring the voltage and holding the current fixed. Or I can measure the current and hold the voltage fixed, and that would be chronoamperometry. So those both methods you're going to use. The other method you're going to use is what's known as cyclic voltammetry. And in this case, it's a case where you're sweeping the potential in time. So if I plot potential versus time, what it looks like is this. It's a triangle sweep, right? So I'm varying the potential in time, and then I go to a certain value and I vary it back. And it's a linear sweep across potential with respect to time. And what you'll get is a response like this for at least, say, the ferrocene-ferrocenium redox couple. And we can understand how this works by first thinking about where do we begin with the potential. We begin at what's known as the open circuit potential, the potential at which no current is flowing. This is very easy to measure. It's just one button on your potentiostat. Because we're at a significant under potential to the value necessary for this reaction, we observe no Faradaic current, but we do observe that capacitive current. It's just not shown here, but it's a small value of the baseline. As we scan further, we're going to actually begin to oxidize, or in this case reduce, reduce the molecule of interest. I guess it's oxidizing the molecule of interest. And then eventually you're going to get to a peak. Now, why do you get to a peak, right? Because eventually, as you start to oxidize a lot of the molecules of interest, because they're in solution, you're going to deplete the number of them that are near the electrode. By virtue of depleting the number of them that are the electrode, you're going to eventually get to a point where that depletion window gets larger and larger. It takes longer and longer for stuff to get to the electrode surface to be oxidized or reduced. Remember that the current is telling you the rate of electron flow per unit time. So if molecules have to go farther to get to the electrode, the rate at which they get reduced is slower, because it took them longer to get there. As a result, the current declines in time. Now, if I go back over the other area, I eventually am going to get to a situation where I'm now able to reverse oxidize all those reduced molecules I made to the surface, or reduce the ones that I oxidize to the surface. And that causes an opposite current. And then when I go back after that, even that gets depleted to the surface. So characteristic features of here can be understood by understanding the mix between the rate of the reaction being controlled by the current. So let's consider a case where you have an irreversible reaction, right? What I mean by an irreversible reaction is that these are the reactions we really care about, right? So the thing I described up there with that nice little duck-looking thing is the most boring cyclical thermodynamic. If you're doing that, you're not doing modern science electrochemistry, although you often need to do that to be able to know what you're measuring, right? To know how to calibrate your value, right? What we would care about is really hard reactions, like taking CO2 to fuel, or taking protons to H2, or taking O2 to water, right? And these are hard reactions, which means they're kinetically difficult. Or in other words, if you have a catalyst to do them, they'll be done in an irreversible fashion. So, if we're doing irreversible reaction chemistry, you can think about the overall landscape of how that's occurring in this sort of a rough zone diagram. So, as I polarize, this is just like what we saw earlier, right? This is an irreversible reaction, so at very low overpotential, I get very little current because I don't have much driving force. As I increase the overpotential, I get to a region that's known as activation control. Activation control meaning right now I have not increased the rate so much that I'm limited by the rate of molecules coming to the electron surface. Rather, I'm in a region where I've gotten the rate to go up a little bit by increasing the driving force, but the rate is still limited by the rate of turnover of the molecules at the surface sites. Okay, so let me say that again. Right here, we're not limited by the rate of stuff coming to the electron. We're limited by the rate of the stuff that's at the electron converting from reactant to product. It could be H plus going to H2, or CO2 going to a fuel, or O2 going to water. The specific case doesn't matter. But this is what's known as activation control, because the activated processes, the things that have reaction barriers at the surface, are determining the rate. As I get into an even higher overpotential, my expectation, if everything came to the surface at infinite speed, would be that the rate would keep going up exponentially, right? That's what the Volmer equations tell me, right? Which is that as I increase overpotential, I'm lowering the barrier for that reaction. Okay, sorry about that. So if you increase the voltage more, right, if you did a thought experiment where things could come to the surface with infinite speed, you would expect an exponentially rising plot. So just keep on going, right? Of course, that's unrealistic, right? Eventually, I'm going to get to a region where the rate of this reaction is so high that I'm not limited by the rate of turnover at the active sites. Those have been exponentially exploded away. I'm instead limited now by the rate of stuff coming to the electron. And because of that, I'm going to get to a region called mixed control. Mixed control meaning, in part, the rate is determined by the potential. But eventually I'm going to get to a region where some of it is being controlled by the rate of stuff coming to the electron. Because there's mixed control, the real line, the solid, doesn't match the expected dot. You'll do an analysis in this lab that's known as foot of the wave analysis. And that basically says, if I look right at the foot of this catalytic wave, I'm in a region where I'm more or less controlled purely by activation control. And so from that I can understand something about the mechanism of the reaction, whereas if I were to explore it up here, I would be limited predominantly by the rate of stuff coming to the electrode, not the rate of the turn. Of course, eventually you're going to get to a region where the only thing that determines the rate is the rate of stuff coming to the electrode, and then going to more and more overpotential is not going to make any difference in the world. Does this picture make sense? Does this, if you understand this, you'll understand at a very, very fundamental level what 99.99% of all electrochemical scientists in the world don't get, right? Because most people think about this very phenomenologically, but this is really how to understand this. Okay, I should say one other thing, right? If you are sweeping the potential, you're going to get a transient rise relative to the steady state value. So what I showed before is what's known as steady state. That's if I took each individual point and waited until the system equilibrated. If I do a sweep, right, I'm going to overshoot because when I first scan, there's going to be more stuff at the electrode than when I scan back. Right? There's a transient behavior. If I superimpose on this the fact that there's a double layer charging current, remember there's this non-Faradaic process where I have to move electrons to the surface and countervailing ions to the surface to support an increasingly larger field, then this looks like the overall shape that will look a lot like the face of the baby. So why exactly is it that there's a log linear scaling between overpotential and reaction rate? So this is a funny plot, right? This is what's known as a Tafel plot. You'll use this. But what a Tafel plot essentially is on the x-axis is a plot of the log of the reaction rate, right? Remember, reaction rate in the world of electrochemistry is synonymous with the current that's flowing per area per unit time. And that's charge per unit area per unit time, which is current per area, right? And as a plot of the log scale. So this is very high currents, 10 to the minus 3, versus 10 to the minus 6, which is very low current, or very low rate. This is increasing overpotential. So good catalysts are where on this plot? What I want for a good catalyst is a very, very high rate and a very low overpotential. A bad catalyst with something with a very, very high overpotential and a very low rate. So which corners of these plots are good and bad catalysts? Where are the good catalysts? They're over here, right? So that's why this is a funny plot, right? Mostly on plots, good stuff is to the top and to the right. And bad stuff is at the bottom and to the left. On these plots, good stuff is on the bottom and to the right. Bad stuff is at the top and to the left. So you have to appreciate why that is, right? So a good catalyst means that I have lines that are over here. Very high current, very low overpotential. Bad catalyst, very high overpotential, very low current. Does everyone get that? So why is this actually occurring? So this is a hypothetical reaction when I happen to work on graduate school. We will not be focusing per se on this reaction, but the other reaction that's relevant to this, which is taking protons H2, is the entire sort of last half of this ladder. So what's basically happening here is that as I apply increasing overpotential, some fraction of that overpotential is going into lowering the activation barrier. And how is the activation barrier related to the reaction rate? What is the equation that describes the relationship between the rate constant and the activation barrier? You remember what that is? The Arrhenius equation, the iron equation, right? So essentially, the activation barrier, delta G double dagger, is logarithmically related to the rate constant. So if I vary the activation barrier, I'm going to get a logarithmic change in the reaction rate. And that's fundamentally where the scaling arises. So the last section of this is really a case study in hydrogen evolution, but I want to give enough time for it. Marius, could we introduce a smaller but one more class period?
Absolutely, anytime after this Thursday.
Okay, I don't want to short shrift this because this will actually help you a lot with writing your ladder portion of your lab manual, and ultimately, my goal is not to rush. My goal is to make sure you guys understand this. So this was a lot of material. I appreciate that. This is a subject. I often say that teaching electrochemistry to people who've never had it before is a lot like teaching organic chemistry to someone who doesn't know what that is. Right? So I appreciate that this is a lot of material, and it's a lot of material that you may not have necessarily seen. So I please ask that you spend a little bit of time over the next couple of days. Could we do it on Thursday?
Actually, no.
Okay.
But we could do it next Tuesday.
Next
Tuesday. Or next Thursday.
Next Thursday won't work for me, but next Tuesday probably will work.
Sure.
Yeah. Okay. So let's come back and convene again next Tuesday. And in the intermediate time, I ask that you look at the slides that I post, which will be all of these with the audio, and essentially internalize as much as you can with the dialogue as to what all of this means, right? And then we'll use this as the basis next Tuesday, right? Yeah. And I will go through, this will be a much shorter class period, where we'll just go through a little bit more of the details of why kinetics are the way they are, and talk specifically about the case of hydrogen generation, because it's an easy example, and will relate a lot to the latter portion of it, where you'll specifically look at that reaction. And what we did in that portion of the lab, and this is deliberate, right? I really feel the best way to learn about science is to just learn actual science. So we're going to let you create your own catalyst and evaluate your own catalyst and determine the mechanism of what you make, right? And so what you're going to do is very much, literally, very similar to what we do in the lab.
and what people in the lab do everywhere around the world who are trying to develop new technologies for these devices. And so you'll get a chance to experience that, but you'll also experience with that, and there's a lot of things to consider. So we're going to go over that a little bit on next Tuesday and consider possible mechanistic models for a very simple reaction taking proton solution, which itself you can see is very powerful. Okay, so with that I want to break here and we can